Hello and welcome to the Unit 12 podcast on Section 25.2. Today we're going to be talking about radioactive decay. I'm Mr. Sakaguchi,
And I am Mr. Lin.
and let's get started. Nuclear stability. So, whether or not something emits radioactivity is dependent upon the stability of the nucleus. And remember, from way back in Unit 1, most of the atom's mass is in the nucleus itself, and we know that the nucleus contains protons and neutrons, and sometimes these are referred to as nucleons.
Now, since protons are all positively charged, they're going to want to repel each other, and there's got to be something that's counteracting this force, and this is known as the strong nuclear force. Because the protons want to separate from each other, the strong nuclear force acts as a glue to hold them close together, extremely closely together, and enough so to overcome this repulsion that the protons have. Neutrons help in this in that it puts a little bit of distance between the protons, and so when you have a balance between the protons and the neutrons, you can have a stable nucleus. But in a nuclear reaction, this tends to fall apart.
Correct. So this is something we had hinted at earlier in a previous podcast, but this proton to neutron ratio kind of helps us predict how stable a nuclei will be for a particular isotope. So when we're looking at small atoms, with atomic numbers less than 20, we find that the optimal or most stable ratio is 1-to-1 neutron to proton.
And this is why you wind up seeing most atomic masses being double the atomic number. But as you increase as you go up the periodic table, this ratio changes and it starts becoming greater than 1. And as this occurs, you start losing nuclear stability.
And so we see that the ratio increases to about 1.5 neutrons to every 1 proton. We can plot this ratio, and you see this on the figure on the right, and we call this plot where the plot represents these are the most stable isotopes, these are the band of stability, and these are where the most stable nuclei for isotopes are found. And as we said before, any isotopes above or below or beyond the band of stability will more than likely emit radiation and work their way back towards the band.
Right.
There are different types of radioactive decay. We talked about alpha emissions and beta emissions before. These were the most common types of decay, but there are also some other ones to be aware of, and there are more that go beyond what we're talking about here, but these are a couple other ones that are mentioned in the book. One is known as a positron emission, and we'll talk more about these in a moment, and one is also known as electron capture. These do happen, but they're much less prevalent than your traditional alpha, beta, and gamma emissions.
Right.
With respect to beta decay, beta emissions basically increase the stability in an unstable isotope by reducing the number of neutrons, and as a result of decay, it moves closer to the band of stability as a result.
So what happens here is a neutron turns into a proton to move it towards closer towards that band of stability, and a side effect of that is an electron gets shot out.
And with respect to this nuclear reaction, notice how the mass numbers are always equal on both sides of the arrow, and notice how the atomic number, or the number of protons, is also equal on both sides of the arrow. So 131 on the left-hand side, 131 on the right-hand side, 53 here, 54 plus -1 is also equal to 53.
Right.
You want to do alpha?
Okay, so with alpha decay, same concept, except it's a different particle that's being emitted. Here we have this usually occurs with nuclei that have more than 83 protons or beyond element 83. Here we have a change in both protons and neutrons. Both of them need to be reduced in this kind of decay to achieve stability. So as you can see here, an alpha particle is essentially a helium atom. And as you do the math here, you've got 222 for your atomic mass. And then after the radioactive decay occurs, you still have 4 plus 218 makes 222. Down here with the atomic number, with a number of protons, same deal, 88, and then yields 2 plus 86, still 88 particles, so conservation of mass is still being followed.
Right, and this is, again, the end result is to hopefully become a little bit more stable. Positron emission. This is the decay process that results in a positron leaving the nucleus. A positron basically has the same mass as an electron, but has a charge of a proton. And it's another way to increase neutrons if the ratio is deficient in neutrons. So this is our positron here. It looks like an electron, but notice the +1 here instead of the -1. And also notice how the mass number doesn't change, but notice how the atomic number goes down by 1.
Right. So
Okay.
this is a way to increase the number of neutrons.
This, what you see here, is a neutrino, but we're not going to worry about that.
Right. Lastly, we've got electron capture, and this is what happens when an electron bombards a substance, and as a result of that electron entering the substance, you wind up with a change in charge, and to counteract that, you wind up having to decrease your number of protons, as is shown down here. So this is, again, increase the number of neutrons, decrease the number of protons, and it's when an electron bombards a substance and makes it more stable that way.
Yeah, you can almost think of this as the opposite of a beta emission,
Right.
where you have a proton basically turning into a neutron, because notice how the mass number doesn't change. And again, the only emission you get is a neutrino, but again, we're not going to worry about that since it has no charge.
Right. Thing about neutrinos, neutrinos, really quick, just a side note, billions, trillions, infinite number of them are constantly passing through the Earth, but we don't notice it because they have no charge, they don't affect us, they pass right through you this very moment. It's just kind of neat, and, you know.
Okay,
Yeah.
it's good to know. One of the other things you're going to have to be able to do is write out nuclear equations and balance them. And hopefully, if you've followed along with today's lecture, you'll notice that when we're doing things like this, the total numbers on the completed side should equal the total numbers on the incomplete side. So if this is 94, 2 plus what is 94? If this is 242, 4 plus what is 242. And the way you identify the element is whatever this lower number is what the atomic number is for that element.
Right, so you'll know where to find the symbol. Another thing to be aware of is if you see the coefficient here, this multiplies all of the numbers associated with it. Now here we've got a neutron that's got a mass of 1, so really what's changing here is 3 times 1 and also 3 times 0, which is still 0, but if you run into one where it's not, then you'll know to multiply the whole thing. It's just distributed through both of the numbers, and you can still solve it the same through the rest of the way.
Yeah, so for this one, because it's a 3 here, it's not 260, it's actually 262.
Right.
For the total mass number on the right-hand side for this reaction. And we'd like you to complete these.
Right. So expect these to be turned in tomorrow, or checked in tomorrow.
Is that it, I think?
I think there's one more.
Oh, wait, one more, sorry. We also have the radioactive decay series. What we find is that for most of our radioisotopes, they undergo not just one radioactive decay reaction, they go through several. And what's interesting is that they always go through, depending on the particular isotope, it always goes through the same series of decay steps. So what you see in this figure here is the decay series for uranium-238, thorium-232, and plutonium-239.
And those are the 3 most common radioactive substances that we deal with in the scientific community.
And you'll notice that no matter what isotope as long as it's uranium-238, these are the steps that it'll always go through.
Don't worry, you do not have to memorize these. Just know that they exist.
It's just something, and this is something we can take advantage of later.
Right.
And now that's it.